Here we have a question on a series RLC circuit. Please read the question yourself before looking at my solution. So we have a series R, L and C connected to a 1000-volt 50 Hertz frequency. Frequency is constant. The resistance is 100 ohm constant. The capacitive impedance is minus J200 ohm, also constant at this frequency of 50 Hertz. The inductance is variable. Suppose the impedance of the inductor is XL bar and the voltage across the inductor is VL bar plus minus. Okay. Then we have to find the value of this voltage VL at the resonance condition. Now at resonance, we know that the impedance of this inductor should be equal and opposite to the impedance of this capacitor. So XL therefore should be equal to J200 ohm at resonance. And then these two impedances will cancel each other. How much current will flow here? This current will be 1000-volt supply voltage divided by 100 ohm resistance, because XL and XC will cancel each other. Now, if this current is multiplied with the impedance of the inductor, that is J200 ohm, that will be equal to VL bar, inductor voltage. So this will be 2000 volt multiplied by J. So the value of this voltage is 2000 volt at resonance. Now there is a second part of this question, and here this inductor is varied to get maximum value of the voltage VL across the inductor. When will we get maximum voltage across the inductor? Let us see. First, how much is this current? How much is the magnitude of this current? We can write that current as the ratio of this supply voltage divided by the magnitude of the total series impedance, which is 100 squared plus XL minus 200 whole squared. Okay, so this is the magnitude of the current here. Now if I multiply this with XL, that is the inductive impedance magnitude, then this will give us the magnitude of the inductor voltage in general for any value of this inductance. Now we want this value to be maximum. Let me write this in this way: 1000 divided by under root 100 squared plus XL minus 200 whole squared, and here in the numerator I have an XL. Let me divide the numerator and the denominator with XL, so there won't be any XL in the numerator, and here I will put XL squared, and this will become 1 minus 200 by XL whole square. Okay. So this voltage expression can also be written in this way. Now we want maximum value for this. That means we want minimum value for this quantity. When this quantity in the denominator is minimum, this voltage will be maximum. Now this can be written as 100 squared by XL squared plus, if you expand this, you will get 200 squared by XL squared minus 400 by XL plus 1. This is the quantity inside this green circle. And now we want to minimize this quantity. So minimize this function, the function of XL. Now here you can see that this 1 is a constant, so it doesn't matter. Then we can divide this entire quantity by 100. Okay, so I get rid of some zeros. Okay, therefore this will be equivalent to minimizing 100 plus 400 500 divided by XL squared minus 4 by XL. Now to minimize this quantity as a function of XL, what do we need to do? Take a derivative with respect to XL. Okay, so the derivative with respect to XL will be minus 2 into 500 divided by XL cube minus 4 into minus 1 by XL squared. Okay, so this is the derivative with respect to XL, and this should be equal to 0 for the minima. Now this would imply that XL is equal to 250. Now I leave it as an exercise for you to calculate the second derivative of this quantity at XL equal to 250 and check that at this point the second derivative is positive, ensuring that for XL equal to 250 this quantity is minimum. That means this quantity is minimum, so this voltage will be maximum at XL equal to 250. So then from here, what can we conclude? The maximum value of the voltage VL will be equal to this quantity. Let me copy and we have to put XL equal to 250 here. So if I put 250, so into 250, and then if I put 250 here, this will become 50 squared. Okay, now if you simplify this will be equal to approximately 2236. So this will be in volt. This is the maximum value of the voltage across the inductor.